Greetings. Welcome back to AP Physics C, Electricity and Magnetism, where I'm covering Unit 4 over, magnetism. And in this chapter, we are covering magnetic forces, namely on moving charges and currents in wires. In the last video, I covered how permanent magnets work and the fields that they generate, as well as kind of the main differences between magnetic fields and electric fields. Now in this video, we're going to go into more detail on how exactly those fields exert forces on other things. So let's get going. And to start, I'm going to kind of call back on the permanent magnets from the last video by first starting with mostly the obvious, what most of us experience with magnets already, which is that permanent magnets, I guess most of us hopefully know, exert forces on each other through either attraction or repulsion. So if you hold two north poles of a magnet together, then they'll repel each other. If you hold a north pole and a south pole together, then they'll attract. So like poles repel and opposite poles attract. Now that's all one thing, but something less obvious is a few curious observations that physicists made, especially in the 1800s. Now the first one is, how do we make sense of magnets deflecting cathode rays? See, J.J. Thomson and a few other physicists in the late 1890s were studying an interesting device called a cathode ray tube. And cathode ray tubes were used probably most famously by physicists like J.J. Thomson to prove the existence of the electron. See, a cathode ray tube is a device that flings a beam of negative charge, which we later found to be electrons, out of a high voltage cathode on the left side over here, towards an opposite positively charged anode on the other side. Doing this created a beam of electrons that flows from left to right in this picture right here. Now, to do this, you need a relatively high voltage, and so that's kind of what took so long for us to figure this out. And it's worth noting that the beam you see here isn't actually a visible beam of electrons. Rather, there's a special screen here that's illuminating when the beam of electrons happens to hit it. Now, the curious thing observed here by a few physicists was that if you took a magnet and you brought it near the cathode ray tube, especially in this orientation, pictured here, the magnetic field would deflect the cathode ray either upwards or downwards, depending on which pole was facing the beam in that scenario. And so this kind of perplexed a few people, but it did give us valuable insight into what magnetic fields were able to exert forces on, other than, other magnets. So this observation is one thing, but even before that, there were also some observations made by Hans Christian Ørsted and André Maria Ampere on the effect that electric currents had on magnetic needles. See, if you have a wire, and let's say the current is flowing towards you, so out of the screen here, they found that in that orientation, if you were to arrange compasses around that wire, that it would exert kind of a circular force on each of the compasses surrounding the wire. So depending on where the compass was, the magnetic field would exert a different direction of force in a circular pattern. If instead we had a wire kind of oriented like this, and you placed a compass on top of that wire, then when a current was directed upwards, in this case, then it would be observed that the compass would deflect from left to right. So an upward current would produce a rightward magnetic force on the compass. All of this aside, not only did this give valuable insight into how magnetic forces operated, but it did also give us valuable insight into the fields that currents were generating in these scenarios. And so all of this put together led to some pretty valuable observations that gave us insight into magnetic force. And so the main thing was to think about what these observations all had in common and what we could take away from those. So from all of those observations, we got the magnetic force, or otherwise known as the Lorentz force, after it was fully developed. So the main thing to take away from all of this is that in both of those scenarios, it was moving charges that were responsible for all of these forces happening. And so in general, we identified that magnetic forces are exerted namely on moving charged objects. So, for example, magnetic fields exert forces on charged particles like moving protons and electrons, like we saw with the cathode ray, and forces are also exerted on a steady flow of electrons, like current in a wire. So in his study of the electron, J.J. Thomson, famous for the discovery of the electron, introduced the first model for determining the force on particles in an external magnetic field. So that equation is the one you see at the top of the slide here. This is the official equation for magnetic force on a moving charge, otherwise known as the Lorentz force. And it says that the magnetic force due to some field is the charge experiencing that force in coulombs times the velocity of the charge as a vector multiplied or cross-producted by the magnetic field strength and direction at some location. Now, it's worth noting that this equation isn't the original one officially that J.J. Thomson made. It was later corrected by Oliver Heaviside and Hendrik Lorentz, hence Lorentz force. But this equation was kind of the complete version that was fit inside a collection of other very famous equations that make up electricity and magnetism. So the main thing with this equation is that it is a cross product of velocity and magnetic field vectors. So that means that if the magnetic field is constant, because all of these vectors are perpendicular to each other, none of them are ever going to help each other out directly. So the work done by the magnetic force on a charge is always going to be zero, just like we established in the last video, because both velocity and magnetic field and I guess the resulting force are always perpendicular to each other. So none of them are ever going to give a little extra oomph to the other vector. So it's charge times velocity times magnetic field strength. And keep in mind that because it's a cross product, you can always provide this equation in alternative forms based on other notations for cross products, like QVB sine theta. Now also, because it's a cross product, this is a great time to remind us ourselves of the lovely right-hand rule. So because the magnetic force is a cross product, you can use a right-hand rule or a left-hand rule to determine the directions of the quantities involved. So I've got our equation up here for reference, and I've got ourselves a nice right hand. And I'm going to use this guide to kind of walk you through exactly how to set up the right-hand rule for magnetic force. So you might raise your eyebrow at the fact that I mentioned a left-hand rule as well. That's because in this case, again, we have positive charges and negative charges, and they play by different rules. So in general, you can use your right hand for positive moving charges and conventional currents in wires. That's because conventional current is treated as a movement of positive charge. Now, otherwise, you should use your left hand for negative moving charges, because any force that they experience is going to be opposite the convention that we use for positive charges. So with that said, here's the general step-by-step procedure that I recommend you take in order to orient your hand correctly and get the correct direction of force in the end. First, I recommend you start with your pointer finger. So you should establish the direction of motion of the charge wherever it is in the problem, and take your pointer finger and align it in that direction. So say the charge is moving off to the left, you should align your pointer finger to the left and keep it locked in place. Once you've done that, the next step is to extend your middle finger out perpendicular from your index finger, like so. Whoop, there we go. And keeping your index finger pointed and locked in to the left direction, now take your middle finger and rotate along that index finger axis until your middle finger is aligned in the correct direction of the magnetic field, right? And once your middle finger is aligned in the direction of the magnetic field, you can now extend your thumb, and your thumb will now point in the direction of the magnetic force exerted by that magnetic field. So to reiterate, establish the direction of motion with your index finger, lock that axis in, extend your middle finger out perpendicular to your index finger, and then rotate your hand along that pointer axis until your magnetic field is in the correct position, and then extend your thumb and it will correctly point in the direction of the magnetic force. And again, if you have a negative charge moving around, then you should use your left hand in order to establish the magnetic force that it will experience, because it will always be opposite of what the positive charge will experience. All right, so to get some practice with this, I'm going to go back to that picture of the cathode ray tube. So in this case, keep in mind that it is negative charges, electrons, that are flying out from the left side towards the right side. So in this case, you should use your left hand in this case in order to determine the force that it's experiencing correctly. Now, in this case, we also know and see in the picture here that there's a north pole of a magnet facing towards the side. So in this case, the field lines would be pointing into the screen or into the side of the cathode ray tube. So in this case, you're going to first establish your left hand's pointer finger in the direction of the electrons, which would be from left to right. So your left hand index finger should be pointing to the right. And then you'll take your middle finger and extend it and point it perpendicular to the pointer finger in the direction of the magnetic field lines. In this case, the magnetic field lines should be pointing into the screen. So with your index finger pointing to the right, you will point your middle finger into the screen, and then you can extend your thumb and it will point downwards in the direction of the deflection that the electrons are experiencing. So if you've done all of that right, your thumb should be pointing downwards in the direction of the deflection that the electrons are experiencing in the cathode ray tube. So that's just one example, but there are a lot of other opportunities to practice all of those left and right hand rule gymnastics in the future. But before we do that, I first want to go over something that we haven't really gotten a chance to talk about in Physics C yet, which is how to represent 3D vectors on a page. On a page, generally, up till now, we've been representing vectors in some combination of left-right vectors in the x direction, up and down vectors in the y direction. But because now we have to represent vectors in a third direction as well, I'm going to introduce to you the third direction, which is into and out of the page, otherwise known as the z direction. So in this picture over here, you get a pretty good representation of what those sorts of vectors look like. So the first one is vectors pointing into the page. Those vectors are represented by x's. And a good way to think about them, and why I have pictures of literal arrows up here, is because in a way you can think of the x convention that we use here as imagining an arrow that's flying away from you into the page. When you're looking at an arrow flying away from you, you can imagine you're looking at the back of the arrow where all of the feathers, the fletching is. And so when you're drawing X's, you're looking at the literal back of an arrow flying away from you into the page. So that would be represented by the current I over here. Conversely, vectors pointing out of the page are represented by dots. I'll move out of the way here. There we go. So just like with an X representing the back of an arrow, if an arrow is flying towards you, which is unfortunate, then you're staring at the literal arrowhead. And so in this case, imagine that an arrow is flying towards you. You're not really seeing the feathers, you're seeing the arrowhead, which would just look like a dot looking at it head on. And so vectors pointing out of the page are represented by dots, just like the B field over here. And so it's a convention just to be aware of. You'll see this notation a lot when you're looking at diagrams given to you on physics problems and especially on the AP tests. So it's something worth keeping in mind, and it's a good way to keep track of not only vectors in the x and y direction, but the z direction as well. So with that, we're going to get some practice with magnetic force, as well as a few more right-hand rule examples to be aware of. So let's get to it. Alrighty, so I've got two examples here, both involving magnetic force on a moving charge, one involving a proton and one involving an electron. So keep in mind that opposite charge is going to mean we have different hand rules to consider. So with this first one, we've got a proton traveling to the right along the x-axis, and it enters a region where there's a magnetic field of magnitude 2.5 teslas directed upwards along the y-axis. And so if the proton experiences this magnetic force, our goal is to find the speed of the proton. So the first thing I note here is it's a lot of text, a lot of descriptions, and if you can unpack all of that in your head, then great. But if not, and you're feeling like you're having trouble visualizing what's going on, if it's tricky, draw a picture. So I'm going to do that. I'm going to draw a positive charge here, just to remind myself that it is positive. And it says it's traveling to the right along the x-axis. So I'll just draw a little velocity vector going that way. And we say it's in a region where there's a magnetic field directed upwards along the y-axis. So I will draw little magnetic field lines pointing upwards in this case. Doesn't have to be anything crazy, nothing fancy, just, to help us out with figuring out our hand rules. And so the last thing, I guess, is just establish that it's the velocity here that's our big unknown. So we should know where how much force is already acting on it. So in this case, now that we've got kind of a lay of the land, the next thing is to write out our relevant equation. The magnetic force on a moving charge is given by the charge times the cross product of the velocity with the magnetic field. Now, this form of the equation looks a lot scarier than it really needs to be, so we can make a lot of simplifications to this. So the first thing to note is that a cross product can always be rewritten as Q times V times B, so the magnitudes of the three quantities, times the sine of the angle between the two crossed values. So that would be the angle between velocity and magnetic field here. Now, in this case, we have a pretty good lay of the land here, so we can get a feel for what that angle is. Here, the magnetic field's traveling up, the velocity is traveling to the right, so the angle between these two is directly 90 degrees. That means that sine here is going to be sine of 90, and sine of 90 degrees is equivalent to 1. So we don't really need to worry about the angle here. So that means our magnetic force equation simplifies to Q times V times B, and that's basically the end of it. We can call it there. This is basically the nicest this equation will ever be, QVB. So now we just need to think about the quantities we have. Note that there's no charge given to us in the text of the problem. That's because AP expects you to know that the charge on a proton is the elementary charge. So down here, recall that the charge on a proton or an electron is always 1.6 times 10 to the negative 19 coulombs. Now, beyond that, we have the magnetic field strength, that's 2.5 Teslas, which is really strong, by the way. And finally, we have the force acting on the particle, which is 3.2 times 10 to the negative 12 newtons, of course. So with all this information, we have basically everything we need to solve for velocity. All we got to do is rearrange. So if we wanted to take this equation and rearrange it to solve for velocity, we would have velocity equaling force divided by QB. And all we really need to do there is plug and chug. So our force is 3.2 times 10 to the negative 12. I'm using my scientific notation shorthand there. And then we're dividing by 1.6 times 10 to the negative 19. It's a terrible E, sorry. Times a magnetic field strength of 2.5 Teslas. And if we put all that together in our calculator, we end up with a speed for this proton of 8 times 10 to the 6 meters per second. So 8 million meters per second. That is a zoom-in proton if I've ever seen one. Wow. Now, here, the problem doesn't explicitly tell us to find the direction, so we can kind of get away with ignoring that. But unfortunately, on this next problem here, we will need to do some right-hand rules. So if you want to practice that with this one, be my guest, but I will save that for the next one here. So this next one here involves an electron and an electron beam, just like the cathode ray tube. So you can consider this to be a cathode ray tube problem. And it experiences a downward force of 2 times 10 to the negative 14 newtons, really small, while traveling in a magnetic field of 8.3 times 10 to the negative 2 Teslas, westwards. Important. So our goal here is to figure out the magnitude and direction of the velocity of that electron beam, or I guess we could say a single electron within that beam. So just like last time, there's no picture here, so it's always good practice to just draw a picture. Here, I like to draw electrons as blue, so I'll start with an electron, and we'll imagine that this electron is, well, we don't really know where its velocity is headed, so we can't really assume the direction of that. We just kind of need this electron to be here. What we do know is that it experiences a downward force, so I will draw the magnetic force on it acting downwards, like so. And we also know that the magnetic field in this case is acting westwards, so I will draw just a couple of westward field lines. These are not exactly the most straight arrows, but you know, it gets the job done, like so. And that magnetic field is acting west. So with this, we have our lay of the land, and we can go ahead and solve for the magnitude right off the bat. See, our magnetic force equation, again, is QV cross B. And in this case, we can simplify that again to QVB sine theta. And just like last time, there's no really funky angles here. Everything's at right angles to each other, as it seems. So we can go ahead and assume that this sine theta isn't really going to be as important in this problem. If there's no funky angle really given to you, always assume that you can just kind of use QVB, and that sine theta will become 1. All right, so just like last time, our velocity is our goal, so we're solving for magnetic force divided by charge times magnetic field strength. And in this case, we're given the force, so that's going to be 2 times 10 to the negative 14 newtons. We have a magnetic field strength of 8.3 times 10 to the negative 2 Teslas, sorry. And let's see, finally we have an electron. So we can say that the charge on an electron is, again, the elementary charge, the magnitude of it at least, which is 1.6 times 10 to the negative 19 coulombs. And with that, we have enough information to solve. So here, our velocity, if we're plugging everything in, will be 2, I'll use my shorthand, times 10 to the negative 14 divided by our charge, which is 1.6 times 10 to the negative 19 coulombs times 8.3 times, tempting myself too much, times 10 to the negative 2. And so putting all that into your calculator, you find that these electrons are traveling with a speed of 1.51 times 10 to the 6 meters per second. So 1.51 million meters per second. Again, these electrons are... Now, keep in mind that is only the speed. So we need to find the direction in this case as well. So this is a bit of a tricky one because so far I've been instructing you to always align your pointer finger first with the direction of the velocity of the charge. In this case, we can't really do that, can we? So in this case, you kind of just need to pick a random other finger to start with as your axis, and then you just kind of rotate everything around from there. And in this case, it's the pointer finger that you want to be your result in the end. So in this case, I personally would probably recommend starting with your thumb, just because it's the most easily controllable thing, and you can always align your hand with the magnetic field. So I'm going to have a little other screen popping up showing my perspective, since obviously my webcam doesn't do much good here. But the way that I would handle this is I would take my thumb, I would align it downwards first to set my axis in place, and then I would extend my middle finger out. And my goal here is, well, the magnetic field is pointing to the left. And so I need to align my left hand middle finger with the leftward direction. Once I've got that, I should have a thumb pointing downwards and a middle finger pointing to the left. And in this case, the result is my pointer finger, which will now extend. My pointer finger should now be pointing at you from my webcam, but you should be pointing into your screen if you're doing this along with me. And so in this case, the direction of the velocity of these electrons is into the screen or into the page. That is what velocity these need if this specific combination of vectors is given to you. So thumb down, middle finger to the left, pointer finger should be pointing into the screen by the left hand rule, because remember, this is a negative charge. So that just about does it. I will say this is 1.51 times 10 to the 6 meters per second into the screen or into the page. And that is 2 examples of magnetic force on moving charges. All right, what's next? Now, the last thing I want to talk about is the other scenario. So far, we've been focused on moving charges. So I figured I'd talk about continuous moving charges, otherwise known as current. So current is by definition the motion of charge, so it's got to experience a magnetic force as well. And so if we imagine a wire of length L carrying some current I through a uniform magnetic field, B, it's going to experience a force given by this formula here. So the magnetic force on a current carrying wire is the current I, which is given in amps, times the length of wire in the field, specifically in the field. If it's outside of the field, it will not experience a force. And interestingly, the length of the wire is cross-producted with the magnetic field strength, which magnetic field also being a vector. And that's given in Teslas. Now it's worth noting that the equation I have at the top of the slide here, that's the one given to you on the AP Physics C formula sheet. Note that this one has an integral form, and that's for specific scenarios in which the magnetic field strength is changing through the length of the wire. I'll give a few examples of that in later videos, but for this one, we're just going to focus on assuming that the magnetic field strength is uniform, in which case we can use this form. So a few takeaways from this one. First, we use this form and we use a right-hand rule for this equation because conventional current represents the motion of positive charges. So there's no need to use the left hand here. We're not imagining that current is the flow of electrons, even though it is. Here, we'll use our right hand to represent this force. So you point your right index finger in the direction of current to get your magnetic force. And so the other thing that might strike you as odd is that it's not the current that's the vector here, it's the length of the wire. And in this version of the equation, current and length of wire as vectors are pretty interchangeable. Really, the only reason why this notation takes precedence over current having direction is because of this integral form over here, where it's not really the current that's being split into tiny intervals, it's the length of wire being split into tiny intervals just for calculus reasons. But in general, you can kind of leave them interchangeably. The current goes in the same direction as the wire in most cases, so it doesn't really matter too much. Just keep those directions in mind. So with that, I'm going to do one more example, just showing you how this works with a wire, and then we will call it a day on this video. So let's get to it. Alrighty, so one more quick problem here, just involving the force on a current carrying wire. Another interesting thing about this problem is it throws a little bit of a wrench in things by finally throwing in a funky angle. So now we can't necessarily ignore that sine theta as a part of the cross product. So the first thing is to go ahead and read what's available to you in the problem. We've got a wire carrying a current of 2 amps, so we know that. And it's inside of a magnetic field with a strength of 3 Teslas. It's really strong. And it makes an angle of 30 degrees with the field direction. So our goal here is to find the force per unit length on the wire and to state the direction of the force on the wire. So force per unit length here means that we don't really need to worry about the length of the wire. Instead, we're looking for force over length. So we can just kind of divide the length in our equation over to the other side and call it a day. So the first thing is we do have a picture here. We don't need to draw one ourselves. And so if a picture is given to you, go ahead and take advantage of it. Draw all over it. So in this case, I'm going to draw my own personal vector representing the current. I'll do that in blue like this. And then our field is going from left to right in this case. So I'm going to sprout the field from where I sprouted the current vector from, like so. Now the advantage of doing that is to help yourself make sense of the right-hand rule structures that you're going to need to set up. And before I get to that, I'll go ahead and write out our equation. So we have force on our wire is equal to the current times the length of the wire crossed with the magnetic field. And again, I and L are kind of interchangeable as which one is the direction. Here, because we're going to be dividing L over to get force per unit length, we'll go ahead and assume that I is the one that is the vector here. Now, the thing is, because it's a cross product, another way to write this and to make sense of it is that it's really the part of I or B that's perpendicular to the other that makes up the cross product. So another way to write this would be the current that's perpendicular to B times L is the magnetic force. That's because, again, a cross product is meant to only multiply the part of one of these vectors that's perpendicular to the other together. And so in this case, we need to identify, let's say, the part of the current that's perpendicular to the magnetic field. And so to do this, I will go ahead and find, well, it seems like here we just need to isolate the part of this current that's traveling up away from the magnetic field, like so. That is going to be our I perpendicular. And so it's that component in particular that we need to find and multiply with our magnetic field strength. That's what gives us the cross product. And so to do that, well, we know that this current here appears to be making a 30-degree angle with, oh, sorry, it's in white, a 30-degree angle with our magnetic field direction. So the opposite side here indicates we will be needing to find the sine of 30 degrees. That is going to give us our vertical component. So now that we've done all of that, we can say, well, comfortably now, it's going to be I times magnetic field strength times the length of the wire, which we will divide over, times the sine of our given angle. That's what's going to give us the proper force and the proper component. So to do that, now we're going to go ahead and divide our length over. So it'll be FB over L. And so everything on the other side is going to give us our answer. It's going to be current times the magnetic field strength times the sine of our given angle equals our force per unit length. And so in this case, current was given as 2 amps. Our magnetic field strength was 3 Teslas. And our angle given was 30 degrees, so sine of 30. And in this case, you can make very short work of this calculation because sine of 30 degrees very commonly is just 1/2. And so 1/2 times 2 cancels each other out. And so we can go ahead and just knock out the sine 30 and the 2. And if you were to run that all through your calculator, regardless, you would end up with a force per unit length of 3 newtons per meter. So there's 3 newtons for every meter of wire that exists in this magnetic field, like so. All right, so that gives us the magnitude. So the last thing here is we need the direction. And so to do this, this is kind of the hard part with right-hand ruling, is when things aren't at perfect 90-degree angles with each other. And that won't always happen. So here, right-hand rule still applies, and I'm going to do my best to show how you can make sense of this, both with the actual directions and with the projections that we drew already. So in this case, it's a conventional current, so we're going to use our right hand. And in this case, again, I recommend starting with your pointer finger if you already know the direction of the current. So we're going to point our index finger in the direction of the current, kind of up and to the right. And then we're going to take our magnetic field and we're going to rotate our hand so that our middle finger is aligned with the magnetic field. Keep in mind now, your current has probably skewed off from the direction you originally had it in. Now in this case, I'm kind of having to contort my hand a little bit here. You might be too. In this case, we want our current to again line with the direction of the wire. So in this case, regardless of how you set this up, if you point your thumb out now, you're going to end up with your thumb pointing into the screen with your right hand. So that means my thumb should be pointing at you at this point. Keep in mind that I'm mirrored if you're looking at my webcam. Now, that sight might seem a little odd, but it's worth keeping in mind that even if your index finger kind of goes off at an angle like this, all that's doing vector-wise is reducing the length of your thumb, if you could imagine that. And another way to think about it is our index finger should be pointing in the direction of current that's perpendicular to the magnetic field. In other words, our index finger, if we're going by pure 90-degree angles, should be pointing upwards in this case, since that's the direction of our current that was perpendicular to the magnetic field lines. It's very weird, but that's just how cross products work. And so in this case, again, magnetic field middle finger should be pointing to the right, index finger should be pointing up or along the direction of the wire, and regardless of how you do that, your thumb will now point into the screen. So the right hand rule dictates that our force here will be pointing into the page, just like the last problem we did. All right, and that is basically all there is to it. From here, it's mostly just going to take practice and finagling and contorting your hand in mysterious ways to work with the right hand rule. But really, everything you need is already done. So thank you very much for watching. I hope this helped with coming to grips with the basics of magnetic force, and we will take things further in the future. Thank you very much for watching, and I hope you have a good one. Farewell.